right, and we are back. So this course is not a statistics course, but when you're working with big data sets, it's inherently necessary, and actually it's always a good idea in general to start to perform or think about what are some statistical analysis that you can perform on your data set. We need to be able to measure data, import data, plot data, do all of the things that we want to do with it, but we also have to determine, is our data distinct? Is our data different? Are we actually measuring something, or is it just within our error bars, effectively? So those are the questions that we need to start to ask ourselves as we kind of pour through some of these data sets. So we're going to start off with some of the basics. Again, it's a quick overview just to kind of get you going, and then in other courses you can kind of supplement this as well. So we're going to be looking at terms like Gaussian, central limit theorem, z-score, t-tables, ANOVA analysis, et cetera, et cetera, et cetera. So first thing, sample versus a population. So if I have a bag of 10 to the 4 marbles, and I've normally distributed it, you could look at some different function as well. But I can go ahead and I could start to think about, and you can just see an example of those, but anyways, this is my population. I want to measure, again, the population is the total number of basically potential measurements effectively in your system. You're never really going to know the exact number of populations. So for example, if you're measuring the temperature in a room, you're never going to measure all the possible potential temperatures. But instead, we're going to look at an example. And we're going to take a sample of that to approximate as best as we can our population. So for example, this average 10 meters for the diameter of the marbles, standard deviation of approximately approximately 1. So if I take one random sample, that is not a good approximation of this mean, is it? Or that population. If I take 10, I'm getting a little closer. If I take 50, I'm getting even closer, right here. If I take 500, I'm really getting close. So as we gather more samples, we can better approximate our population. And one of the ways, and actually this is basically a histogram, we've kind of run into those when we're plotting before, but what we're looking at here is basically a distribution, and this distribution looks Gaussian. A Gaussian distribution is your bell-shaped function. It is a function of the mean and the standard deviation of that population. So I can develop what's called my PDF, or my paired distribution function. My PDF basically allows me to look at and actually start to kind of develop confidence intervals. Confidence intervals, and you can see that 90% of our data, confidence intervals are essentially what we're looking at is where do I expect to find 90% of my data. So if I integrate my PDF function, my Gaussian distribution from -infinity to infinity, that value will be 1. Because I cannot tell you the probability to measure a single measurement, but between two bounds, I can tell you that probability. And the Gaussian is beautiful because it is symmetric. So 0 to infinity, I could do from -infinity to infinity. 0, excuse me. And you can see the integral of that is a half. And again, what we're saying here is that our measurand, we expect a measurement, if I'm measuring the length of a beam, I need that measurement to fall between -infinity and infinity. So there is a 100% chance that I will measure a value of a beam between -infinity and infinity. It better be. I could also look at and see for this value of z, which again is a function of these, again, fitting parameters, and x is our measurand, what is the value of z that gives me my 90% confidence interval? What about 95? 96, 1.96. So we start to see what bounds, what values of z are we going to see or expect to find 95% of our data set. Now, this is all great, but when you're doing this, you're assuming that the population is a Gaussian. But oftentimes, there's lots of distributions that are not Gaussian. So they can be, again, most of them are Gaussian, but they could be, here's an example of Gaussian distribution. And actually you could improve their Gaussian by looking at these fits. But they could be a uniform distribution, right? Perfectly random. So that population looks very different. And so the question is, how do we then use the same type of basically statistical analysis? Obviously this is not Gaussian. I don't have a function that describes this. But central limit theorem allows us to do a really cool thing. It allows us to get rid of this idea or this problem of well, how do I deal with the statistics of my system? How do I basically get rid of this assumption that essentially that I have to have my population be Gaussianly distributed? And more importantly, I want to be able to estimate some bounds or some estimate of what my true population mean is, because that is a difficult thing to do. So one of the cool things is if I start to kind of choose randomly, choose some, again, out of this this uniform distribution, give me a sample size of 6, and I can calculate my mean. And then if I start to do that, if I do that multiple times, so here, take this sample and look at the means. These are the 2 means from that random sample. If I do that, nothing really changes here. If I look at the distribution of my means now, so the means of each of the samples, nothing really happens. If I do 10 of those measurements, it's starting to look a little more Gaussian. If I do 30 of those measurements, very interesting. What if I do 100 of these measurements? Super Gaussian. What if I make this 30? Very Gaussian again, or I can do 50. So very, 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 very Gaussian. And I can do the same thing with a chi-square. So a chi-square test, the means are Gaussianly distributed. So the means, if I have a larger sample size of my means and I look at the distribution of my means, those are Gaussianly distributed. So it doesn't matter about my population, it matters that the distribution of my means will be Gaussian. And therefore I could estimate my confidence intervals using an expression that looks basically like this, where it's mu equals x bar, my mean, plus or minus, plus minus, basically my confidence interval z value c over 2 times sx over square root. But anyways, we'll see that more in class. But that's basically what we're working with here. And this gives me, again, an estimate of my true population mean. Great. You can do the same thing for small sample sizes as well. So we're going to get into that next time. This all holds, this type of analysis holds for sample sizes that are large, i.e. greater than 30. So now, small sample size and less than 30, what are we going to do? Well, we'll see you in the next video. Thanks. Bye.